लाइन में नहीं था, भीड़ नहीं थी, दीदी की सोसाइटी में जे खा गए थे, 4 बात सुना के आते। बाबूजी तो सुनने लगा, मैच देखेंगे। हाँ,
Good afternoon, sir.
Good afternoon. So we'll start in a while.
नहीं
Others might join.
दीदी बोली तो ठीक है, कोई बात नहीं, कल का ब्लड टेस्ट कराएंगे, फिर शाम को जरूर डॉक्टर के पास। लेकिन हमको तो कोई तकलीफ नहीं था, तकलीफ की वजह से डॉक्टर डर के ऐसे हमको बोली थी दीदी। और आज का रात निकल जाए, कल सुबह ब्लड टेस्ट कराएंगे सुबह ही।
कौन कर रहा है? भाई कौन? मैं पापा बात कर रहा हूँ।
नहीं, पापा को दे दो। हाँ भैया, हम लोग का कुछ नहीं हो रहा है भैया।
Okay. Good evening.
Good afternoon, sir. Good afternoon. Yeah.
Let's start now. Welcome once again
Welcome, sir.
for our last session, probably for this course. So, we had covered 12 sessions so far for all the week respectively, and so this is an extra session. So, I'll try to summarize the whole course for in this quick session, and then we'll discuss whatever if anyone has any doubts, or I'll try to solve some assignment problems. So just for practice and for preparation for the exam.
Sir, one thing. What about crank Nicholson method? It was mentioned there in the last lecture. What is
Yes. So it's a kind of it's a time marching scheme. So basically, we when we discretize in time, basically our time dependent equations. So we use the finite difference method.
yeah?
So
UI, IJ, I plus one. That one, no? I think.
yes. So basically, we use an approximation. For, let me write it here somewhere. So if we have a solution, so I am writing in terms of theta,
Yes, sir.
un plus 1 plus un equals to delta t. So if we take theta as half,
Okay,
that
sir.
is known as Crank-Nicholson method.
In terms of geometry, we say that it is a. Suppose that I have a quadrilateral mesh.
Yes,
We give the ij to the central node, and I plus one. This was nomenclature that you used in mathematics.
yes.
It's same, no?
That's right. So it's kind of like we have solution here. It's kind of an average of this, right?
Ah, hmm.
Un, this is un plus 1.
Yes, sir.
So this x is actually for us represents time.
Okay.
Yes, yeah, this is Crank Nicholson here. So let's quickly go through all the week's content, then we'll start
Yes, sir.
some problems. Okay, so I hope your preparation is going fine. When is the exam, by the way?
28th.
28. Okay. So welcome everyone. So the course is the finite element method, variational methods to computer programming. And we started first this course by understanding the basic concept of variational calculus.
Yes.
So variational calculus is something which is used to solve minimization problems. So
Yes.
if we have a functional,
Mm-hmm.
uh, where if a functional which is a function of of a sum function, basically, so that's how a functional is defined. uh, if we want to minimize the value of that functional, what should be the form of what should be the that definition of that function?
It should be a function should be bilinear and symmetric, and LVs will be linear.
No, that's something different. That's not that will come later probably. So right now I am trying to define the problem. What
Yeah,
is
sir, we are able to then only minimization problem exists now.
yeah, you're right. So you're right, but that is they're in different context. Right now I was trying to tell something else. Basically, definition of a minimization problem.
If AUV is bilinear
Yes.
and symmetric and LV is linear, we have to first know that we can, by variational method, we have to discretize into AUV and LV is equal to LV.
Okay.
AUV is the use the variation, V is the variation, and use my uh, deformation or temperature, whatever you can say.
Yes.
So first, we have to first Euler-Lagrange equation to minimize it.
Yes. So yeah, basically we define the functional in the form, what you're saying, right? IV minimize V such that half of V minus LE LV, right?
Yes, sir.
Right, that's right. So this, for this, for that, this should be bilinear symmetric,
Yes, sir.
and this should be linear.
Linear.
That's right. Yeah. So how do we define a functional?
Function of a function.
Yeah, exactly. So it's basically a mapping of the function yx to a scalar constant. So the functional can comprise of the independent variable and the dependent variable, as well as its n number of derivatives.
Yes, sir.
So so minimization. There are certain examples for the minimization problem, such as we studied Brachiostrone problem, and we in some session we also discussed uh, minimization of the travel path between 2 points problem. All
Yes, sir.
such problems can be formed in terms of this, formulated in terms of this minimization problem. So how do we minimize this? So first of all, we consider we write a function, the function yx, in terms of the minimum function yx plus its variation, or that we usually call as delta y, or
Mhm.
here we've defined epsilon eta x, which is an arbitrary function.
So we write it as using the Euler language equation. We can minimize it.
Yes, yes. So that's how we approach the Euler-Lagrange equation.
So del f by del y minus dy dx of del f by del y
Yeah,
dash
yeah. So we define our functional in terms of
f x y.
any function
Yeah.
fy, and this fy tilde is actually equal to
Well,
the actual minimum function plus some variation.
yes, sir.
So the first variation of this with respect to with respect to this variation y delta y equals 0. This is a
Zero.
necessary condition for the minimum, for the extremum to exist. So then we further derive this equation of for the necessary condition for the first variation. So then we get our Euler-Lagrange equation. So whatever the functional is defined as, we can straight away, to minimize this, to uh, to minimize this value, the value of y can be derived from this Euler-Lagrange equation.
Yes.
So this will give us a differential equation, also what we call a strong form.
Yes, sir. You're right.
Okay. So using so basically a fundamental target of variational mechanics for us here is to uh, to get a strong form or the equation of motion from the given minimization problem. And this Euler-Lagrange equation can be expanded to a multiple function problem or multivariable functional,
Mhm.
and even for a higher order derivative functional.
So it will plus minus and plus minus. So
Yes, exactly. Just a minute. Then next thing, there's something known as a variational statement. So from our strong form, from a strong form, we can approach to a form of the problem which is known as weak form, or that we also know as variational statement. So basically, we multiply the whole the strong form or the governing equation, differential equation, with the a weight function, or which is in which is also known as the variation of the variable, primary variable, and that integral statement would give us the variational statement basically, or the weak form. So if we are given this equation here, the minus d square u by dx square equals to fx, we multiply it by a weight function w, and perform integration by parts, we'll get this uh, these two terms, an equation in terms of integral statement. And here this first term first integral, which we write as aw, is our bilinear symmetric term, and the other part is our linear term. And then
Yes.
we also discuss what are the criteria for any operator to be bilinear or linear and symmetric. So for linearity, we need to check two main criteria, that these two condition here. If there is any operator t over variable u, then t of u plus 1 plus u2 equals to should be equal to tu1 plus tu2. And if lambda is a scalar, t lambda u should be equal to lambda times tu. That confirms the linearity of the operator. Then bilinearity then means there are two operator t two variables in an operator t u v, then both should be independently linear. And symmetry we know. So ultimately, from our minimization problem, we can you can use the Euler-Lagrange equation to get to the strong form, and then using the weighted residual statement, or we can achieve the weak form or the variational statement. Then if in a given weak form, these two conditions are satisfied, that the operator a is bilinear and symmetric, and the operator l is linear, then we can also use the given weak form to again arrive at our minimization problem. So all all three forms of problem definition are equivalent. And if this these bilinearity symmetric conditions are satisfied. So that we had discussed earlier also, if we are given any the weak form, the bilinear and linear term of the weak form, we can use them to define our minimization problem. Okay, so
Hello.
let's, yes,
Sir, we'll be replacing when you have to check it that our system AUV and LV satisfied.
sorry,
AUV and LV satisfied, that is bilinear and symmetric, and LV is linear.
yes,
Then to convert into minimization problem, we have to go for LVV. Half of AVV minus LVV. That's it.
yes, yes.
Is equal to something zero.
No, 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 this won't be equal to 0. So this will be our f, this term.
Ah. Mm-hmm.
We define our integral as x1 to x2
Okay.
f of, we can write v.
Okay. Okay.
So this is the definition of fv here. Okay. Then again, you can take fb and get your Euler-Lagrange equation.
Sure.
So yeah, that's that about the problem definition. Now, how do we solve this problem? So uh, this course is all about the approximate solution method. So that mainly we will be covering finite element method, but there are certain methods that are prelude to FEM that we
Mm.
discuss in this course. So first of all, the weighted residual method. So in weighted residual method, we multiply by the residual, or the given equation. If we write this equation, uh, if we write the whole equation on one side plus fx, this should ideally be equal to 0. But if we approximate our solution as something, then this shouldn't be equal to 0. This should be equal to some error, or what we call residue here.
Ah.
So to minimize this error across the domain, we multiply it by some functions and integrate over the domain. So based on the type of function that we are choosing, there are different methods. If the weight function is equal to the, so we approximate the solution as some constant ai times phi I. This summation is intended here plus phi. So if our weight functions are same as these approximation function which we have used for the solution, then we call this as the Galerkin method.
Looking at that.
And if this weight function are equal to the linear operator, the bilinear operator applied. I'm sorry, not bilinear operator. This differential operator that is part of the differential equation. Then that this is called least square method. Basically, it's kind of a squaring of this term. And in collocation method, we choose certain specific points and we evaluate the value of of the function on those points. So then next we had the Rayleigh-Ritz method. So in Rayleigh-Ritz method, also the approach is similar to weight residual. We multiply the residual with the weight function, but we also reduce the differentiability requirement of that of the our solution basically. So here we perform integration by part and we write the weak form of the problem, and then we assume the solution. So one thing about the choice of these approximation functions is that these function the phi 1 phi 2 should satisfy the homogeneous form of the boundary condition, and while phi naught should satisfy the boundary condition itself. So what's the difference between the two?
Essential boundary conditions should be satisfied by our phi naught.
Yeah, that's right. So that is one difference between the Rayleigh-Ritz method and the weighted residual method. That in the Rayleigh-Ritz method, only essential boundary condition should be satisfied, while in weighted residual, both essential as well as Neumann boundary condition should be satisfied.
Yeah.
And but phi one, phi two, these other function should should satisfy the homogeneous form of the boundary condition. That means if our given boundary condition is u at 0 equals 5, so the so phi naught should satisfy this, but phi 1 should satisfy this. Okay, so that at x equals to 0, we'll only be left with phi naught, right? The other phi 1 phi 2 would become 0. Okay.
What are the limits if I have a bond, if I have a say function phi I,
Yes.
if I have a limits 2 to 5, how to assume the same function?
Sorry.
If I have the limits of my bound as 2 to 5,
Okay. The you mean the domain limit
yes sir,
2 to 5?
then how will we take the say function phi naught or yeah
That depends on the boundary condition. So if you're saying that your domain is
2 to 5, yeah,
2 to 5, right? So we should be given either u or du by dx here.
like ux1 is u1, sir,
Okay.
ux2 is u2,
U that means u at x1 equals u1,
u1,
u at x2 equals to u2. Yes.
and x1 is the variation is from u has a variation from x1 to x2. Okay,
Yes.
so it is said that we have to bound that phi naught as u1 into x2 minus x by x2 minus x1 plus u2 into x minus x1 by x2 minus x1.
So you mean phi naught should
And
give us at x1 should give us u1, and phi naught at x2 should give us u2.
Yes, sir.
Yes, yes, yes.
And
So
then phi 1x will be x minus x1 into x minus x2, and phi 2x will be x minus x2 x1 whole square into x minus x2. If we proceed ahead, we can go ahead.
sorry, I didn't understand the question here.
How do we like take the safe functions? Suppose there are three variations. Suppose that my un is equal to cj phi j plus phi naught x,
Okay, okay,
and j is equal to 1 to n. Let's take j is equal to 1 to 2.
okay. Yeah. So so this function should give us u1 at x1 and u2 at x2. So basically some function x1 it's u1. So for our convenience we'll assume
So it is said that
initial
un should
condition.
satisfy both the essential boundary conditions.
Yes, yes.
Am I right, sir?
Yeah, yeah, those both are essential boundary conditions.
So if I have ux1 equal to u1, then my phi 1 and phi 2 should satisfy this.
No, your phi 1 and phi 2 should satisfy this. Phi 1 at x1 should be 0. Getting it?
You're right. You're right. Yeah. Yeah.
And same for phi 1 at x2 and same for phi 1 at x1 and phi 1 at x2.
Yes, sir.
Okay. But phi naught we'll define as some we'll find if we'll find the equation of this line, is it
You're right. Why not to satisfy the essential boundary condition? Means like
yes,
if I
yes.
give, yes, sir. Right.
So as I have written here in this equation here, so it if one of the limit is x equals 0, we are given a rigid boundary condition x equals 0. So there phi 1 and phi 2 would become automatically become 0, leaving only phi naught.
Yeah. Right.
So this automatically takes care of the boundary condition.
Yes.
Okay. So yeah, that's it for week one. We will quickly go through everything. Or if you have any specific doubts for any part, we can straight away go to that. If anyone
So
has
I had
any.
asked a question about uh, assignment 4.
Yes, assignment 4.
So actually, what happened that they have derived a matrix. Can I show you that?
Sure, sure.
Wait, sir. Let's wait.
Sure, sure, no problem.
What happens, sir? I had asked a question like there were derivation. If I show you this by, wait a second, sir. Go to this one. Yeah. So I'm sharing my system now, sir.
You can share your screen if you want.
Yeah, yeah, I'm sharing it now.
Sure. I'll also check it here. Meanwhile, it's assignment 4, right?
See, sir.
Yes.
So if I see this book,
Yes,
for bar element, they have derived it as E with 3L 71 minus 8. Okay, but for me it was coming some. For me it was coming this one, but from the answers it was marked wrong because of another, that they have derived 7 as in the bottom and 16 in the between.
it should be 7 at the bottom and 16 in between. As far as I remember, it's 16 in between. Have you derived it yourself?
Yeah, yeah, yeah. I've derived it.
So you're getting same as given what is given here.
Yes, yes, it's a book with me now, and they have derived it completely. It's book by Liu.
Is there by any chance they have taken a different order for a direction for the node assignment? No. Can it be? Like, have they taken the left node as node 1, middle node as node 2, right node as node 3?
That might be one thing that might have taken that.
Yeah, can you check if you have the book?
I asked regularly, but I didn't get the answer. It's okay.
Uh,
It's okay. One doubt I had this way. Okay.
yeah.
Okay,
Can
so continue.
yeah.
Uh,
Okay, so yeah. Then we'll quickly start with the proper FEM, and the main theme of this course.
yes,
So
sir.
in FEM, we follow certain steps. Okay, let me share my screen for just a minute. Yeah. So in
Mm.
FEM, we follow certain steps. First, we perform discretization, or we break the domains into several parts. And before that, also there's one thing that we have to define the problem, right? And then we take its find its weak form. And the purpose of arriving to the weak form is, why do we do that?
To solve the problem, because to reduce the order for differential equation. Yeah.
Yes, right, exactly. So that we can approximate a solution with a lower degree polynomial. That
Hmm.
things can be easier for us. Then we after discretization, discretization we define the type of elements. It's linear, quadratic, or even in the 2D, 3D, we have different types of element. We have triangular elements, quadratic elements, like that. And then we have to define their shape function or the approximation function as well. Then we have to calculate the element level equation. So whatever our weak form equation is, we we uh, we solve it for a given element. We approximate we approximate the solution for that element using the approximation function, and we get some algebraic equation for that element. Those are known as the element level equations. Then we perform the assembly. We combine the different element equations to a global system of equations. Uh, then we apply the boundary conditions to reduce our to basically make our given determinant, or sorry, the matrix uh, uh, matrix as having a unique solution. So then only when we apply boundary condition, we'll have a matrix with a unique solution, or the system of equation with a unique solution. Then we then solve the given equations, and we do post processing if required. So then we did some discrete type of problems, spring type. We'll quickly skip through it. And one thing that is used essential for uh, uh, doing our performing these steps or in FEM is to perform numerical integration. So we arrive at a, a weak form, which is nothing but integral statement, right? We have integral terms occurring there. So to solve those integrals, we at some point at basic 1D level simple elements, it is very much possible to solve that manually using conventional integration method. But it in practical scenarios, when we where we have uh, thousands of elements, and we have complicated elements, we have complicated shape function approximation function, there the integrals are not so direct to solve them using conventional methods. So we perform numerical integration. And one thing great about numerical integration is that it is much easier to write the algorithm for numerical integration. So in numerical integration, we mainly use Gauss quadrature rule. So for Gauss quadrature rule to be applied, our integral limit should be between -1 to +1, and then we can approximate the integral uh, as the value of the integrand at certain points multiplied by the respective weights. So based on the level of complexity or the degree of the polynomial in the of the integrand, we can choose the number of points that are required to get an accurate integral value. So one thing, the important features of these quadrature points is that they are not same as nodes. First of all, for Gauss quadrature rule, there are certain rules. I think Newton codes has the Gauss quadrature same as nodes, and then these points are unequally spaced. And the important thing is that the integral limit should be between -1 to +1. What if our given integral is not between -1 to +1? Then we perform mapping of this integral. So we we have to use a transformation function which gives us x equals to L here for whatever the zeta value is at -1, and then m x equals to m for zeta equals to +1. This will give us a function, and then we can easily transform our given integral from the x coordinate system to the to zeta coordinate system. So these are some these quadrature points are derived actually. So these are defined for us. So we can just directly use these quadrature points to get our integral values. And how do we decide the number of points required? This basically depends on the order of polynomial. So if p is the order of polynomial, and for if p plus 1 is even, then the number of quadrature point is p plus 1 by 2, and if p plus 1 is odd, then it's p plus 1 by 2 plus half. So we kind of approximate to the nearest next integer value, basically. That's it. So that's it about the Gauss quadrature or the numerical integration for 1D. Then how do we how do then we demonstrate how do we use FEM to solve a simple differential equation. So here we are given a differential equation, d square u by dx square plus x square by 4 equals 0, and this here u is our primary variable, and we have been given the boundary condition u at 0 equals 3, and the derivative of u at x equals to L is 1. So first thing, we derive our weak form. Then we discretize our domain. So we split the domain of length L into two elements of length L by 2, L by 2. Then then we would need to approximate our given domain or the given element to the standard domain. Why do we do that? Why do we map our physical domain to the standard or the this natural coordinate domain?
Actually, length of elements is 2, -1 to 1. So we simplify our problem. So master element to simplification is quite easy to solve the problem.
Yes. So firstly, as discussed before, we need to perform numerical integration, right? And these numerical integration statements are the numerical integration rule, that is Gauss quadrature rule, is valid for the integration limits of -1 to +1. so it's convenient for us in that sense. And secondly, if we up map all our physical elements to this master domain, then most of the calculation part is quite similar. So most of the things in the in our equation, or the stiffness matrix and force vector would be same, except the Jacobian part for the mapping. So every time we don't need to reevaluate the shape functions for each element. We can just straight away use the shape functions for the master element, and we just need to calculate the Jacobian, which is rather easy to find for each element.
How can we, sir?
Yes.
Suppose that I have my step function in my master domain. Okay.
Yes.
So how do we convert into physical domain step function?
Okay, that's right. So we can simply derive, or actually there's a formula if you want to do it quickly. So
Yes,
if
sir.
we are given, this is xa coordinate, this is xb coordinate of node 1 and 2. So n1 is equals to xb minus x upon xb minus xa, and n2 equals x minus xb, no sorry, xa upon xb minus xa. Okay. So this is the right formula, but I derived it in one of the earlier lectures. Few.
So it is for linear elements,
Yeah, this is for linear elements. Yeah.
and for our quadratic.
Quadratic, also there is, I think, formula. Let me see if I remember it well. It's actually xp minus xa. I can't recall the exact formula for it, but there's a formula. Or simply you can derive it also every time.
We can write it as a1 plus a2, a2x plus a a3x square.
I think
Yeah, 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 exactly.
we use Lagrange
Sorry,
multipliers like for
your
deriving
Mr. Vijay, your voice is breaking. Can you repeat again?
quadratic shape functions. We use that Lagrange multiplier.
Can you repeat, sir?
Yeah, we use this Lagrange like what do they call Lagrange
Yeah, yeah,
polynomials. Will be
yeah,
like
yeah.
x
Lagrange
minus x1,
polynomials.
x minus x2 divided by yeah. For quadratic, like it can be extended to cubic also.
Yeah, yeah, yeah. There was some generalized formula for it, right? What was that? Can you recall that? There's actually a formula for Lagrange polynomials. You
I've
can.
seen that. I faced the difficulty in this when we were asked to solve in terms of physical domain shape
Okay.
functions. That time I had to convert that master domain into a
I
physical
think
domain by manually.
Okay, but those
x
Lagrange
minus xa divided by xp minus xa. Yeah.
x minus, but those Lagrange polynomials are supposed to be for the master domain element, right? Master element, isn't it? Not for any general element. Correct me if I'm wrong.
So what about suppose that I have eta equal to 0 at the center, eta equal to minus 1 at the left end.
And
That will give me the shape function in the master domain, not in that.
uh,
So so we can derive it by say u1 is equal to displacement at one end.
okay, okay, yeah, 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 yeah.
Yeah.
For any random given domain, that method is will never fail, but only thing is that that would be a little time taking. So if
Yeah.
you can't do it every time during your exam.
Yes, sir.
You mean this one, right?
Yes, sir.
And you can just approximate this as a plus bx plus cx square. Just find ABC. That's it. Oh, sorry. Yeah, find ABC in terms of u1, u2, u3, and then you.
And the property of shape function has n1 equal to 0 at other nodes,
Yes, yes.
and it is 1 at first node.
Yeah, yeah. So this is a universal method. This is valid for 1D any order element. This is valid for 2D elements, 3D elements. You can apply this anywhere.
Yeah.
Okay, so yeah, but I think mostly you will need those shape functions for the master domain. So that in that case, your Lagrange polynomial would help you.
Okay.
Okay, so yeah, now we have transformed to our master domain. Then we substitute the approximation function into our weak form,
Hmm.
and we get our uh, stiffness matrix and force vector. So for a two noded linear element, we'll get a 2 by 2 matrix and 2 cross 1 uh, force vector. So this would be the, the given set of equation for a single two noded element. And if we are ca- combining, then if we are assembling the two elements, the equations of the two elements, we need to ensure two main ideas. So firstly, that the the displacement should be continuous. We should maintain the continuity of displacement at the connecting node. So at node 2, the displacement that we'll get from first element and the displacement that we'll get from second element should be equal to 2. That's it. So this equation should be followed, and the force uh, coming from the two elements should be summed up, added up. Okay. Then we, yeah, discuss quadratic elements. So we'll have one extra node and one extra higher degree of polynomial. So I've written the shape functions for the quadratic element for the master domain here.
Hmm.
And uh, we can derive the mapping function from these shape functions also. Actually, they are called shape functions because of this property only. They help to map the physical domain to the master domain.
Hmm.
Then if we'll use the quadratic shape functions, we'll have three equations per element respective to each node, and then same thing, same type of assembly. So that's all for simple 1D FEM. Then we'll quickly discuss some structural problems then we had, discuss in this course. Firstly is the 1D bar problem, for which the governing equation is defined here. So it's a simple straight bar in in only along single one axis. We call that x direction, and u is the displacement of the bar along the x-axis. Then we get the weak form in terms. We write our bilinear linear form, and we substitute our approximation function based on the whatever whatever elements we are going to use, and then we'll get a stiffness matrix, force vector. We can also yeah, we would also want to transform our given integrals in terms of the master domain.
Yeah.
So that can be done by this using this equation, using the Jacobian. Then ultimately, if we have quadratic function, we'll get 3 by 3 three equations per element. Okay, so
Well,
this, yeah.
when we are multiplying this J into a stiffness matrix, I mean,
uh, you mean this J here?
yeah, yeah, yeah. When you are multiplying this in a stiffness matrix derivation,
Yes.
so if I have my mode say functions in my physical domain, I don't need to multiply that.
Yeah, yeah, exactly. That's not required.
Okay,
So that means you can just straight away use this equation
sure.
and go ahead. Only thing is your integral limits would be the limits of the element, physical
Physical.
element itself. Yeah. So this is a statement actually written in with respect to programming information. So how do we if evaluate these things for using a computer program? So we need to evaluate the stiffness matrix and force vector for each element, right? So what special information we need for that element? We actually need the nodes of the nodal coordinate data basically for that element, and then we can use that to get our approximation function. Sorry, the mapping function. We already know the shape function for the master element, which is nj here, and we can use nj. We can multiply these shape functions to the nodal coordinates, and we'll get our mapping function x in terms of zeta, and then we can use that to get our Jacobian. So that's the only information we need for uh, corresponding to an element, and we can get its stiffness matrix and force vector. Then there was special case if we had a bar problem with the spring at one of the end.
Yes, sir.
So if the spring is at either of the end, then we'll simply modify our force vector with by adding the force developed from the displacement at that end. So no matter uh, whatever is happening, either either the bar is expanding towards the spring or away from the spring, we'll always be modifying this term as F2 minus KU2. And because of this modification in the force vector, so we would have some matrix times displacement here. So this is a U2 here. So we would have F2 minus KU2 here, right? So to accommodate this change, we'll just simply, when we move this toward this side of equation, we'll just be adding this K here. Then our equation can be left as it is. This contribution of U2 would just transfer there. So that's
Okay.
how we can just change our stiffness matrix because of this spring. Then if we have spring between two elements, then how it will change effect. So uh,
Positive and negative.
yeah,
One will be compressed, one will be expanded.
yeah, exactly. So yeah, one would be compressed, one would be expanded, and based on that, our stiffness matrix would be changed as this. So this is for element 2, and this is for element 3. No, I mean not element 2 and 3. This is actually element 1 here. This is element 2. This is element 1 here. This is element 2 here. Right. Then we have a truss problem. So
Yes, sir.
truss is basically a
Very
bar in
important.
2D plane. Yeah. So so what a difference it makes than a bar is that it will the deformation would still be in the direction of the bar, but since that bar is now in a 2D plane, then this displacement or the deformation of the bar would have two components, x and y components. So we have the problem of dealing with the special coordinate system, and then transforming the equations to our main standard xy coordinate system. So just to quickly go about that. So if we have if we call that this coordinate the coordinate in terms of the in direction of in the direction of the bar as prime coordinate. So to transform our displacement from prime coordinate to our main xy coordinate, we use this transformation matrix Q. So this had been derived before. So what will happen is that when uh, we'll include this transformation matrix as stiffness matrix, which was again de- we had defined it for so if our bar is in this direction, we know the say for 1D elements, we know that it is actually equal to this, right? But this is in the direction, this prime coordinate direction. So in order to transform it to our main xy direction, we just need to multiply it with this qt and q transformation matrix basically. So when we'll do that, we'll have this 4 cross 4 matrix K, which is this matrix. I think if in your exam such complicated matrix would be probably given to you.
It will be given.
I hope so, but bit better to
Ready with it.
either way, it's derivable also, right? You if
Yeah,
you
yeah.
know a q, you can straight away derive it. And not every time you will have this simple 1D linear element matrix K. So it depends on Ke prime also, what you'll get here at the end.
So
So to get the stiffness matrix for the problem, this is the direct method, or you can derive it using this qt K prime times q. And for same thing you'll do for the force vector. You will For prime coordinate we'll have, I think it was something by fe by 2 1 1, right, something like that. Then we'll use this transformation again. We'll multiply this by qt. We'll get a 4 cross 1 matrix. This is actually 4 cross 2. This is 2 cross 1. So we'll get a 4 cross 1 matrix. And regarding the point load or the Neumann boundary terms, we can just straight away add the contribution to the respective value. So here sorry, this row represent displacement in for first node in x direction. This is for first node in y direction. This is for second node in x direction. This is for second node in y direction. Right. So corresponding to that, you will add the point load. If it's in first on first node, you will apply somewhere here. If it's in second node, you'll apply somewhere here. If it's in x, then here. If it's in y, then here. If it's in x in 2, then here. If it's in y in here, say 2, then here. Okay, then we had a simple formula to find a stress using our given displacement, our solution that I had written. Anyway, so that's regarding truss. Then next topic was beam problem. So this is the governing equation for beam. So the special thing is now the differential equation is of the fourth order. So then we have four sets of boundary condition here. So at the two end, either we define slope or the moment, and we have to define either the displacement or the transfers or the point load at the two ends. So two boundary condition at one end, two at the other. So for beam element, since now the solution should be continuous with respect to the the solution value displacement w, transfer displacement, as well as its slope dw by dx. So we use something known as the Hermite shape functions here, which we have to derive using I think a lot of equations here. So this function should at one point it should be at node 1 it should be equal to space 1, and at node 1 its derivative should be equal to 1, and again at node 2 it it should be equal to w2 and its derivative should be equal to w2 prime. So then with all this complicated equation we'll get these shape functions. Again, to map the domain, we are still going to use our normal Lagrange shape functions, linear Lagrange shape functions. That point should be noted. So in this in the beam problem, to approximate the solution, we use different approximation functions or polynomials, and to approximate the domain, we or the to map the domain, we use different polynomials. So such kind of formulation. So here, if we are using linear approximation function for mapping the domain, this and for these for approximation the solution, we'll have cubic polynomials here. So this kind of formulation is known as the super parametric formulation, where the order of solution approximation is greater than the order of geometric approximation. And if it would have been reversed, then it would have been subparametric. And if it is equal, then what is it called? Anyone? So then it is called isoparametric
Also
approximation.
parametric, na?
Yeah, yes. Okay, so this is all regarding the mapping of domain, transforming our solution in uh, x x x or the x coordinate system to the zeta coordinate system, master domain. Then after beam elements, we studied frame element. So frame element would couple all the three structure element concept we studied so far. It will act like a truss. So that means 1D bar in a 2D plane, as well as it will also have the property of bending. So it will also be subjected to bending loads. So it will have displacement along the beam, along the direction of the element, and also along the uh, transverse direction of the element, and also rotation degree of freedom. So it will have total 3 degrees of freedom. So we'll couple the uh, so with 3 degree of freedom per elements, right? So coupling all these concepts, we'll have get a 6 by 6 stiffness matrix. So first three components represent node 1, the 3 degree of freedom for node 1, and next three is the 3 degree of freedom for node 2. So it should be noted that we are considering linear approximation here, because we only have two nodes for an element, right? For Lagrange shape function, not for Hermite.
It is 3, na?
3 degrees of freedom.
Yeah, 3 degrees of freedom per node.
Yes.
Two translational, one rotational.
Yeah. Yeah. One degree freedom per node for bar, and 2 degree freedom per for
Beam.
trans.
Yeah.
Okay. Then again for transformation we do the same thing. So it is acting like a truss also, right? So we have to again do the transformation, and here our Q matrix is this. Okay. So then we also uh, dived into certain concept of how to write a code for our FEM problem. So I don't think this part would be really required for the exam. I don't think, right? You won't be required to write code or even use a code to solve the problems, right?
Okay,
Yeah, I'm asking actually. I don't know
I don't think so, sir.
because there you will only be given a calculator for to use for your calculation. I don't
Yeah,
think you'll be given a proper
dashboard
system.
calculator, no?
Yeah, yeah. I don't think you will have any MATLAB enabled system. So we'll save time and go ahead. So 6 week was just revision for basic calculus, basic
Yes, sir.
tensor calculus. So dot product, what is the free index, what is the dummy index in initial notation, how to write basis for a vector, basis and components, what is the Ronica delta, what are its properties, what is the permutation symbol, and what there's an identity to transform from this permutation symbol to Ronica delta, triple product, second order tensor, the gradient divergence curl. Then we had important Gauss. That is the only thing that we'll be using ahead. Gauss divergence theorem to get our weak form. That's it.
It is used to convert the volume integral into the surface integral and vice versa.
Yes, exactly. Okay, then next we started with now 2D FEM. So first we start with scalar field problem. So scalar field means there will be only one
Degree freedom
degree,
per node.
yeah, 1 degree freedom per node. Only one field for the problem. So the classical example is the heat equation. So we have a Laplace term and a heat source term, known as Poisson's equation. We to then we derive its weak form. We multiply a weight function, and we uh, use this Gauss divergence theorem. That's it. We so first we'll have to uh, write this as, I think, something.
Weak form.
Yeah. Okay,
So weak form.
sir. Uh, you're saying something? Think you're muted.
First lecture was Arup Nandi sir, no?
Yes.
He was teaching about variation. Okay,
Yes.
but now that Arup Ganguly sir said that it is weak form. He said with a different weighting method, weighting residual method. Okay, so that was a bit confusing, but we understood that if we have to first reduce the our differential equation into a weak form
Yes.
using the same concept that Nandi sir said.
Yeah. What did he say? Okay, what is the difference
We
between?
directly concluded with a variational method, like a weighted residual method.
Okay.
It was a bit confusing in the initial days, but it was fine later on.
Okay. Fine. Yeah, and the easiest thing that shortcut that I do is just to transfer this derivative over the weight function. You'll with the minus sign you'll get the volume integral term, and remove that derivative term, and with the dot take dot product with the normal vector, you'll get the surface integral term with a plus sign.
Okay.
That's a shortcut you can use in exam. And then again we perform the approximation using piecewise approximation functions
Hmm.
and substitute them in the equation. You'll get our stiffness matrix and force vector. Now, interesting thing, or rather complicated for 2D problems as compared to 1D, is the discretization of the domains. So here, the discretization is not as accurate as can be in 1D. In 1D, there's no error because of that, but in 2D we get a new error that is due to the approximation in discretizing the domain.
Oh.
So in 2D we mainly use two elements, triangular elements or quadratic elements, both with their own advantage and disadvantage. We have had such kind of debate a lot of times. We still have these. So anyways, so if we are using triangular elements, so first we move on to linear triangular elements, for which the approximation function is linear with respect to x and y.
Mhm.
We have this function here, phi1 equals to a0 plus a1 x plus a2y. Then we can uh, derive these or the coefficient of the approximation function using this equation.
Mm.
So this matrix A multiplied by this matrix B. So matrix B is the coefficient of the columns of matrix B are the coefficient of the uh, co- shape functions for each
Yes,
node.
yes, sequence.
So
Yeah.
this is for node 1, this is for node 2, this is for node 3. And A is the rows of matrix A are the coordinates of the triangle, right?
Yes, sir.
With first row is 1
In the
and
physical domain.
yes, in the physical domain. So this is a trick to not a trick. It's a genuine method to uh, find out the approximation function for a physical domain, for any physical domain. So you just need to write this matrix A, which is very straightforward to do, and you find out its inverse. So when you take its inverse, you'll get B, right? Because this is the property of if A and B multiplied together give identity, then both are inverse to each other. So you
Hmm.
find A, you find its inverse, you'll get the column of that inverse will give you the coefficient of the approximation function. Okay, so these are some properties.
What do you mean by C0 continuity and C1 continuity? A little bit. I don't know that.
Yeah, it's somewhat complicated. I think C0 continuity means that its uh, its first derivative is continuous.
Okay.
I think so. Yeah, combination of these polynomials is continuous in the entire domain. Yeah. So these shape functions should be continuous piecewise only, right? So they don't need to be continuous throughout the entire domain, but they should be continuous in the given element, and uh, ultimately the combination should be continuous in the entire domain.
Okay.
PA should be, yeah, and they should be linearly independent and should be complete. Okay. Then to perform the assembly of these uh, two of the equations arising from 2D elements, we really need something known as connectivity matrix. So we actually need the data of the elements. So the data of these elements or the mesh basically includes firstly the nodal coordinate data, and next is the connectivity data to tell us which node, which node number connects together to form an element. So each row represents each element of the mesh, and each column represents the respective local node, the corresponding local node. So suppose if in element 1, the 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 global node 2 is the local node 1 for that element 1, and global node 3 is the local node 2 for that element, and global node 1 is the local node 3 for that element. Likewise, we write the connectivity matrix. So this helps us to know which when we are assembling the stiffness matrix terms for respective elements. So this helps us to know which nodes are connected together and how the contribution would be added to the global stiffness matrix.
There's formula no to 2p minus 1 and 2n minus 1 and 2n to
For
assign the global degrees of freedom. There is a formula to assign 2n minus 1 and 2n.
I don't know about that. I'm not sure.
It was given in the lecture, sir.
Okay, maybe I might have missed that.
If I say this node 1,
Yeah.
if it has 2 degrees of freedom per node,
Yes. Yes.
so 1, 2 is the first two global freedoms.
Yes. Yes.
And if I have node 2, so I'll have 3, 4. So it will be 2 to power 2 minus 1. No, 2 to power 2
Okay. 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 Okay.
and 3 and 4. This is a
We,
formula. This, yeah,
3 and 4 would represent the second node, the 2 degree of freedom of the second node,
yeah.
right?
Similarly, if I have 3 to
Yeah.
a 6 and 5 and 6 will be there.
Yeah. 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 So that is actually this formula is actually for vector field problem, right?
Yes, sir.
Exactly. Okay. Then after assembly, applying the boundary condition is straightforward, the same as we did for 1D. And one thing we discussed before, in 2D elements, we have this discretization error. Then mapping a triangular element. So in triangular, for triangular elements, our master element is this element from the nodes 0, 0, 1, 0, and 0, 1. So for this element, we kind of remember the approximation function. It's quite easy to remember actually. Anyway, I've derived it here. So using these shape functions, we can write the mapping function for this any physical domain to this master element. Okay. Yeah, and then again, so here the Jacobian is now a 2 by 2 cross 2 matrix. Yeah. So yeah, so that's it about this week's. And we move on. Yeah, we discussed this mapping from to master domain. Then we again have to use numerical integration. So in 2D, it's again more complicated. So solving the integral for any random shaped element is much more complicated than 1D. So here we definitely need numerical integration. So again we have Gauss points in 2D and the corresponding weight functions. So these are similar points. Like we have for 1D, if we use 1 point, we just had 0. Now for 2D, if we use 1 point, we have 0 comma 0. And again, we used to have minus 1 by root 3 plus 1 by root 3 for for two nodes for points in 1D, and 2D we'll have a combination of these two values. We have 4 points, 2 cross 2. And here we had also discussed some this method of calculating approximation function by looking at the element, right? Suppose if we want to find the approximation function at this, say this is node 1 here, then we uh, take the equation of line 1 here and equation of line 2 here and multiply it by some constant, and we substitute at node 1 to at which n1 equals to 1, and we'll get the value of this alpha. So likewise we can find the so like if we want to find, this is say 2 3, say this is 4, so n4 would be equal to the equation of, sorry, some constant time, equation of this line 2 into, say this is line 3, and into equation of line 3, right? So this is also a way to find the approximation function, and this is also valid in for any kind of domain, if any physical or master domain, anywhere. You just need to know the equation of line. Okay, then next is the chord elements. So chord elements are in chord elements they the approximation function is bilinear. So it is separately linear in respect to eta and zeta. So again, we have these approximation function master domain. We can do the respective mapping. Then this is the program algorithm. Yeah, that's it. Then okay, then next is the vector field problems in using in 2D FEM. So here our main example was linear elasticity problem in 2D. So in linear elasticity, we have a displacement field having three components mainly: ux, uy, uz. And if we are dealing with only 2D, we consider only two components. Then the gradient tensor of the displacement would be a 3 cross 3 matrix, and strain epsilon is the symmetric component of this gradient tensor. It is defined in this way. Okay, so there's a lot of thing. So we can break down a strain. If we for simple 2D case, if we are only considering strains in only two direction, we can we'll be left with only these three equation, right? And we can break down these three equation into this matrix and vector form. And this operator here is known as symmetric gradient operator. This would be useful for us for deriving when we are writing our weak form. Then the governing equation here for elasticity is our classical equilibrium equation, or it's just simple force balance equation. So this is a generalized form of the equation. So written in terms of indicial notation, then we'll have for 2D case we'll have two coupled equations in terms of the two displacement components. So you see that this is if we combine these three equations in terms of matrix and vectors, we'll have our transpose of symmetric operator that we discussed above. Then we can to transform relate our stress to our displacement or our strain, we use the constitutive relation, which is our Hooke's law, ca- what we study classically. So here D is our fourth. It is in general sense it is a fourth order tensor. So it should ideally have 81 components, but with a lot of symmetry, and we'll we'll finally, by applying all this symmetry, we are finally left with only two components in case of isotropic. Then to reduce a 3D problem into 2D, we consider two special case. One is known as the plane stress case, uh, where we consider the stress in z direction to be zero, while
Yeah.
we'll still have strain in z direction. We can have.
Yes, sir.
So this case is applicable when the thickness of the
Very
of our
small.
surface is very small. Yeah, of our plane is very small. It's kind of a lamina. Then the next is plane strain case, where we consider the strain in uh,
Is
strain in
zero.
z direction zero, and but we can still have stress in z direction.
Okay.
So and this is considered for infinitely long thickness, infinitely large thickness plane. So again, this is our problem definition, our strong form with any boundary condition for any arbitrary domain. So to write weak form, we have a coupled equation. We have two equations. So we, instead of writing one residual, a scalar residual, we have a vector residual here now, r bar, and we multiply it with a vector uh, weight function w
Mm.
bar. So kind of combining the two equations to write the wake form. So
Wait, to give you a call here.
sorry.
Nothing, nothing.
Okay, so yeah, we derive this weak form, and at the end we have gradient of wx multiplied by sigma x bar. We can write this as the symmetric com we yeah we can this right derive we can derive this and write it in terms of the symmetric gradient operator, and we also know that we can write stress equals to this d times strain, and strain is nothing but the symmetric gradient operator applied on displacement. So this is our final weak form. Now, since we have two displacement, two component of the displacement, we'll have to approximate both of them separately using the shape function. So we consider this uh, alpha x1 and alpha y1, the two nodal displacement values in the x and y direction for at node 1. So simultaneously these two values for node 1, then next two for node 2, next two for node 3, next two for node 4. So we can write this. So we know, right, we can write our uex as nie alpha xi and uis again as nie y. So if we want to club these two equations in terms of these matrices, we can write this as here. Okay. So these to write this in short, we write it as here. Now applying a symmetric gradient operator on this matrix of shape function, we get the B matrix, BA matrix. So while writing the code, we saw that there's no direct way of arriving at this matrix. So what we can do is we can get our this n matrix or the gradient of n matrix, and we can use the component of this gradient to write our B matrix. Again, we map using our Jacobian. Okay, yeah, we studied post-processing again. To from displacement to arrive at our strain, we multiply the nodal displacement vector with our B matrix, and to get the stress, we arrive this strain by D matrix. So in a computer program implementation, as told before, we can get our gradient Ni matrix, and from that we can write our B matrix. Then we studied super convergent points. So these are the points where the the derivative of the solution converges fastest. So usually this is the Gauss point. As so we know that the displacement the value of solution converges fast on the nodes, while the value of the derivative of the solution converges faster on the Gauss point. Those are known as super convergent points. So this is used to evaluate the derivative of the solution uh, into as a continuous in a continuous curve, because when we take for linear elements, if we take the derivative of the solution, we get a constant function. So for each element we get a constant, so this kind of a step occurring in the solution, a discontinuity, because we never ensured uh, that the derivative of the solution is also continuous when we're deriving these things. Then next thing is the error in FEM. So there are several ways uh, to like, you can say that to report error kind of. So it's the energy norm, there's error in L2 norm. Then we discuss adaptive refinement. So adaptive refinement is the partial refinement of match in the region where we expecting a higher error, or we need better accuracy in that region.
It consider biasing.
Biasing, biasing also.
As points are there, no? Suppose that I have a biasing of 1, 2, and 3. Suppose that I have a line, or so I can discretize with a number of one will be far off, one will be another will be too far off.
Hmm. Okay, I haven't heard this term with respect to
Bias,
adaptive.
BIAS.
With respect to adaptive refinement, I am not sure about this.
Okay, fine.
Okay. To perform this partial refinement, there are two approaches. First is we calculate the error, and in whichever element we get more error than our limit, then we refine that element. We split it into further more elements. But the issue that arises here is that we are left with a so for so see there are two elements here. So we broke it down into say this, so let this is one element two, other was element two. Now we have broken down to two, three, four, five. So for two, three, four, five, it's not an issue. So this it's still a normal. It's still a normal element, but the element one has a one extra node now. This is known as hanging node. So what we do is for element one we don't consider as a so we don't consider as a degree of freedom at all. We just estimate the solution at U8 as the average between the node 2 and 5. And other method to perform this adaptive refinement is by generating a new mesh altogether with a more refined mesh in the region where we anticipate more error.
Hello, sir.
Yes.
The aspect ratio will differ in there. One will have a greater aspect ratio in comparison to these four, 2, 3, 4, 5.
Aspect ratio also. Why is so? Because right now in this example we have split it into the both the direction
See,
similarly same way.
aspect ratio is given by largest shortest length ratio of this.
Yes, but that didn't change for us here, right? For each element.
180 is there, no? That is creating a problem there.
Yeah, yeah, yeah. Okay. You mean to say, okay, for element one, shortest side become, say, the length between the node 5 and 8.
Yeah.
Okay. Yeah, so that is the issue. That's why we don't consider this node 8 as a degree of freedom here.
For this problem, it is not a big deal, but when we have a complex problem, then it will be a completely messy.
Yes, yes. Right. Okay, so next we have we eigenvalue problems. So eigen means characteristic of a system.
Yes, sir.
So we for this is applied useful for dynamic systems. So for
Hmm.
example, by vibration beam.
Yeah.
So in dynamic system, so we still have the we modify the equations we studied before. So for example, we had this bar equation where we had this Laplace term and a distributed load term f. Now we add the acceleration term here also. That is the dynamic term. Again, in addition to the boundary condition, we'll also have initial condition. I think that is for the time dependent problems. Anyway, so we consider a free vibration problem. That is, we just start with an initial disturbance and make it keep the system free of any external force. So our body the distributed load F would be 0, and there would not be any external point load, that is P. So our equation would be reduced to this.
Hmm.
So we substitute the solution by,
Separation variable.
yeah, separation variable, exactly. Then we get our this equation, which is the equation for auxiliary motion.
Yes, sir.
Then we use derive the same
Um,
thing for FEM. We derive the weak form, and finally we have this equation. So now this is known as the eigenvalue problem, and to derive the eigenvalue, we take the determinant of this k minus omega square m matrix.
Nick.
Then next we discuss a membrane problem. Uh, so again we have this governing equation for membrane. Here C is the wave speed. We again apply a separation variable, get our auxiliary motion equation, find the weak form, and we get our eigenvalue problem. So basically what we need to do is we need to find the K matrix for the system, the M matrix. K is this matrix. K will have some constant times depending on what the equation is.
It is C square, no?
Yeah, depending on the equation. And for M is basically, so the difference, K would have the gradient of shape function and would
Generally,
have,
C square is T by rho only. Don't.
yes, yes. And here M would be, this is
M
Ki,
N I N J. Yeah.
yeah, M would be Nij. So we just need to find these two matrices, and we can use this to get our eigenvalue. Next, we studied the transient problems, time dependent problems. So first we discussed the parabolic PDEs. In parabolic problems, our solution smoothens with respect to time. So for example, the heat conduction, we see that the temperature would smoothen across the domain. It would try to smoothen itself if we apply no source, heat source. So yeah, now we'll have initial condition. We'll need boundary condition, initial condition. Again, we take the weak form. Now when we are doing this substitution, or we're replacing the solution with piecewise polynomials. One thing to be noted is that earlier our no, the nodal the solution at the node points used to be constant before, but now it would be dependent on time, while our shape functions are same as before, dependent only on space coordinate. So now we have the equation of this form. So we have this K matrix, we have alpha, that is solution vector, and we have C matrix times alpha dot, which is the derivative of the solution vector. So now we have to approximate the solution in time. So we use this time marching approximation, and we have,
Crank method.
yeah. So based on this value of mu in this time marching approximation, we have defined the different methods are defined. So if it's mu equals to 1, we have Newton forward method. Yeah, sorry, mu equals 0, we have forward difference method. For half, we have Crank-Nicolson. For 2 by 3, we have Galerkin method. And for 1, we have backward difference method. So regarding forward difference, it's considered to be not very stable. Its stability is bound by some condition. That is, the time step should be less than some critical time step defined by some formula. And while the other methods are unconditionally stable, so they are always stable. And of these methods, the Crank-Nicolson and Galerkin method are the fastest to converge. So like convergence means that as we reduce time step, the solution would be faster to approach to the exact solution. Then next we had hyperbolic PDEs, where the response or the solution oscillate with respect to time. It doesn't smoothen. So there we have the example of the vibration beams. So again we derive the weak form and write the equation in terms of the derivative of the nodal solution with a dot double dot. So now we have second order derivative with respect to time. So we have to perform certain advanced time marching approximation here. So where this is done by Newmark scheme. So what we need to do is we approximate the solution value at next time step using these formula solution and its first derivative with respect to time, and also second derivative finally. Yeah, so what we need to do is we need to write the our equation only in terms of the uh, solution at the next time step, and all other things would be known. Okay, so we replace the a double dot n plus 1 and a dot n plus 1 terms by a n plus 1, a dot n, and a double dot n. So these a this is our main unknown. So we need to boil down our equation to get to become in terms of only this unknown, while all others are known. So finally we write our equation only in terms of a n plus 1, and we break down our equation in this form. Okay. Yeah, one challenge we'll have is when we are uh, so we have to know the solution value at t equals 0 solution and its first derivative with respect to time and second derivative with respect to time. So in hyperbolic problems we are given in initial condition we are given the the value of the solution at t equals 0 and the first derivative with respect to time t equals 0, but we are not given second derivative. So we can find that by applying these values in the equation here using this equation. Okay. And finally, we are about to conclude the discussion on of this course on FEM in 3D domain. So in 3D domain, again we start by discussion on scalar field problem. That is our heat equation. So now it's so problem definition again still same. We only have now we have temperature field that is varying in the z direction also, x, y, and z. Again, to find a weak form, the same approach is used. The difference come in when we are approximating the domain. So now we have to use since the domain is in 3D, we have to use 3D elements. So again, in 3D, we generally use either a tetragonal, the tetrahedral elements, or we use hexahedral elements. So tetrahedral are similar to triangular elements in 2D, and hexahedral are similar to quad elements in 2D. Again, to derive the approximation function for a tetrahedral elements, we apply a similar approach. We write a matrix A using the coordinates of the nodes of the tetrahedral element, and we take its inverse, and the columns of this inverse would give us the coefficient of the each respective shape function for each node. So we can approximate solution in terms of these shape functions, also the respective derivative, and when we then we write substitute this back to get our algebraic equations. Okay, next is 3D elasticity. Now again our governing equation that we had discussed before, sigma ji comma j plus bi equals 0. We now this equation I have will have this equation vector would have three components, so we'll have three equations here, and we'll have three components in the unknown displacement field ux, uy, uz, and we also have moment equation, moment balance equation. So that makes the stress tensor as symmetric. Then we have boundary condition. Now again we have to write the weak form. So here I've written in terms of initial notation. It's the same thing that we discussed before. We took the residue as a vector and the weight function as a vector, and we took the dot product of the two vectors. Same thing here. And we solve it. Then we finally get our weak form asCijkl, the strain times the variation strain, or that is same thing that we discussed in 2D. That is the symmetric gradient operator applied on the weight function here, the vector of weight function. Now, since we have third variable also here, third primary unknown, so we'll have to write the approximation for that too. So again, as we had earlier, for u in this displacement x direction as or ui and I, and for displacement in y direction as vi and I. Here we have displacement in z direction also wi and I, and we can combine these, couple these three equations in terms of this uh, this matrix n, which is 3 cross 12 elements. Okay. Then again, for strain tensor in 3D, we should have 9 components, but since it's a symmetric tensor, we three of the components are same as the other three, so we'll have be reduced with 6 component. So we can write this as a vector, which is known as Voigt notation. So we can again break down it in terms of the B matrix times the displacement vector, the displacement component, the value of the nodes. Okay, then similarly we can do for the variation in strain or the weight function kind of for us here. Okay, so when we substitute these things back in our main equation, we get our algebraic equation. So next for hexahedral, this one earlier we studied for tetrahedral elements where we had only 4 nodes. Now we have hexahedral elements with 8 nodes. So in hexahedral elements, we can the shape function can be derived in the same way we did for 2D. Then we can approximate the Jacobian using the mapping function derived from these shape functions, and we can convert our volume integral. Finally, we discuss the different approaches to solving the equation. So first we have direct solvers, which is Gauss elimination method or LU decomposition. So these method are give us quite accurate solution, but they 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 require more time in processing. While we have some iterative solvers also, such as CG solver, MinRes solver, GMRes solver. So these solvers are quite fast and they are very practically very useful for solving problems with a higher degree of freedom. But the problem with these solvers is that the solution is not very accurate. It is an approximate solution, but it is much more used since the problems in practical applications are rather really complicated ones. So yeah, this ends the discussion on the complete course for of the variational method, FEM variational method to computer programming. If there are any doubts anywhere, we can discuss that. Otherwise, we are almost out of time. We'll try to solve a couple of problems. We'll wait if there's any doubt there. So if there's any specific doubt regarding any assignment question, then you can ask it. Otherwise, I have noted down some assignment problems. If we'll try to quickly go through this in whatever time we have now. So first, in first problem, it was in week one. We are given strong form, so we had to write the variation statement and the minimization problem from that. So I think this is quite rather straightforward. Nothing difficult in that. We write the weighted residual statement. Okay. Light by weight constant W. We perform integration by parts here. Okay, it's better to multiply this equation by R first, then do R. So we have dW by dr, R times d by dr, and we have the boundary term. We have W R lambda. So ultimately we have so we had been given boundary condition for this problem that I missed to write here. So that will make this whole term go to 0. So with this we'll get our bilinear term here, W and here linear term. So now how do we write the minimization problem? Derive this as W minus W half of a W plus L of W. So this would be so this would be a minimization statement. Again, we can perform the minimization, or we can take its first variation. We'll arrive at the equation again. Okay. Now choose the approximation function for the following problem using Rayleigh's method. So, how did we uh, choose the approximation for Rayleigh's method? We check for the boundary condition. Right? Suppose we are approximating the solution as AI Pi plus P naught. So here, suppose let us write it as T1 P1 plus T2 P2 plus P naught. So what boundary condition should P1 satisfy? That P1 at 1 should be 0. And what about P2? Same as P1. P2 at 1 it should be equal 0. And what about phi naught? Phi naught should satisfy the given relational boundary condition. Phi naught at 1 should be equal to 1. Right? So we can just choose some function like Phi naught as x or x square or x cube, anything. It gives us this boundary condition. That x is the most appropriate choice. Okay. When we discuss this thing, find the linear approximation function for a 1D finite element with nodes x equals 1.8, x equals 2.3 to find the linear mapping in Jacobian. Okay, so we discussed before. So the direct formula for that, right? Xb minus x on xl and b would be x minus xl or xb minus x. Here this is xb is 2.3 minus x. 2.3 minus 1.8 is 0.5 and this is equals to minus 1.8. Okay. So linear mapping, we are with the approximation function for standard element R, master element R, this, and the mapping function is equals to xa and 1 cap plus 2 cap. So this will give us our mapping function, and finally the Jacobian. What do we have? Dx by dz. All right. So I think we are pretty much out of time now. Is there any specific you would like to ask? Then we'll discuss it. Otherwise, we can wrap it up. All right, then we'll conclude the session here. I wish you all the best for the exam, and thanks for. I'm sorry, my mic. Okay, I think my mic was off away. I hope the part I discussed before was audible. So we'll discuss. We will end the discussion here, and I wish you all all the very best for the exam. And thank you all for joining the session with me. It was a very insightful and learning journey for me as well. I hope it was the same for you. And I wish you all very best for your future ahead. Thank you so much.